All right, chapter 5 is on chromosome mapping. And the purpose of this chapter is to move on from the situation where two genes are on the same, on different chromosomes. So in the previous chapter, we discussed things like the color of Labrador retrievers. We also discussed things like squash fruit shape and skin color of snakes. And we talked about the fact that two genes can influence the same trait. We've also talked about dihybrid crosses, where two genes influence two different characters. And the idea of this chapter is to move on from the situation that we assumed before, and that was that when you had two genes, they happened to be on the same chromosome or on different chromosomes. So for humans, one of the genes, gene A, might be on chromosome 1, and one of the genes might be on chromosome 2. And because of one of Mendel's laws, we could assume that each one of these gametes, so there's 4 gametes that could be formed, and we assume that each one of those gametes was equally likely. And that is because there is a equal likelihood that this chromosome matches with this chromosome or this chromosome during meiosis. In chapter 5 now, we're going to look at the situation where two genes are on the same chromosome. So if A and B are both on chromosome 1, now that situation no longer holds. So we can no longer assume that each gamete is equally likely to be produced. And so now we have to deal with the fact that genes are linked. So if two genes are on a single pair of homologs, then you have to deal with the case where exchange might not occur. So if there is no exchange whatsoever, and what this essentially means is that there's no crossover during prophase 1, then it's impossible for the gametes to be recombined. So whatever you get from the parents, so this was the chromosome that you got from your mother, this might be the chromosome you got from your father, whatever that original combination was, it would be impossible to switch it around. And so in the case of complete linkage, what you would see is you would have two gametes that have your mother's combination, and then two gametes that have your father's combination. And so what really exists is a combination between these two situations because of the fact that crossover occurs. So we're going to talk about this in more detail. Because there is exchange between these homologous chromosomes, there actually is an in-between situation. So it doesn't actually look like either of these situations. So it doesn't look like independent assortment, and it doesn't look like complete linkage. So by the end of this chapter, you should be able to explain why linkage distorts gamete production. So instead of being all 4 gametes being equally likely to be produced, you have some gametes that are favored. And from this information, you should be able to calculate a mutative measure called the map distance. In the case of having 3 genes, you should be able to establish the order of those genes on a chromosome using information from progeny. And then finally be able to use Punnett square to estimate genotype frequencies for linked genes. And this will be 2 parts. First, we're going to cover 2 linked genes together. And then the second, we'll cover the situation where there's 3 genes on the same chromosome.